All right, everyone, here's our key to the 2017 free response questions. Number 1, we have the height of a tank. It says the function a is continuous and decreases as h increases. That's going to be important. Where a of h is the area of the horizontal cross section of the tank. So on number 1, it says use a left Riemann sum with 3 subintervals indicated by the data in the table to approximate the volume of the tank. And so remember, for an LRAM, if this confuses you, you can go ahead and actually just draw the rectangles. And the points don't have to be perfect, but here's our first point, here's our second point, here's our third point, here's our fourth point. And then you can just draw the rectangles using a LRAM. So we have a rectangle from here to here, but we're going to use the left endpoint like that. And then we have this rectangle, and then we have this rectangle. So the base length right here is the difference between these two things. And then the height is if we're looking from 0 to 2, it's going to be the left endpoint of that interval, so it would be that height. So that's what we're looking for there from a data table. And so I already have the work worked out here, and this is a key that will be shared for you as well. But this way you can just quickly pause it here if you need to see the work, and that'll save time on creating the video. So there's the work for that. Okay, and then on part B, does the approximation in part A overestimate or underestimate the volume of the tank? So since A is a decreasing function, that means the graph looks something like this, as I had somewhat drawn earlier. And so if you find, let's just cut it into 2 rectangles, but if these are our 2 rectangles and you do an LRAM, since it's a decreasing function, that means your left endpoint is higher than your right endpoint, and so your LRAM will be an over approximation or an overestimate, versus an increasing function where your right endpoint is now higher than your left endpoint. And so you get something like this. So now your LRAM would look like this and be these 2 rectangles. Okay, so if you're looking at RAM approximations, overestimates and underestimates are determined by increasing or decreasing. Versus some other things that we have seen is for tangent line approximations, is the function, is your tangent line approximation an overestimate or an underestimate? And that's all based on concavity. I believe that's actually on this set of questions later. So if you draw a concave up curve, anywhere you draw a tangent line, it doesn't matter, as long as you draw it good enough. It has to lie below the curve. So if you have a concave up function and you do a tangent line approximation on a concave up function, then it's an underestimate. If it's concave down, then that's when you have an overestimate, because any tangent line you draw has to be above the curve, except for at the point of tangency where they're actually equal. Okay, so there's 2 different types of estimations we do, and you determine if it's an overestimate or underestimate based on those things right there. So all you had to do is say in 1b, and left Riemann sum is an overestimate because A of h decreases. That's all we're looking for there. Part C, the area of the horizontal cross section at height h feet is modeled by the given function. Based on this model, find the volume of the tank. Okay, so this is our cross section area right here. So that is our cross section area. So you do the integral of cross section area, f of h, times our base length, or our depth, dh, and we're doing that from 0 to 10, and you can just math 9 that, and you can write it exactly as I wrote it right there. Okay, and then in part D, it says water is pumped into the tank when the height of the water is 5 feet. The height is increasing at the rate of 0.26 foot per minute. So we know h prime is equal to 0.26. It's increasing, so it's positive. Using the model from part C, so talking about f of h right here, find the rate at which the volume of the water is changing with respect to time when the height of the water is 5 feet. So we already know from part C that the volume of the water is equal to the integral of f of h dh. But now we're going to go, since the height is changing, we say 0 to h and then do any other variable in here, f of t dt, f of k dk. I think maybe I did on the handwritten one. And then we want to find the rate at which the volume of the water is changing with respect to time. So we're finding dv dt. So remember, the derivative of an integral is the given function with your upper bound plugged in. So it's just f of h, and then times the derivative of the bound that you plugged in. This is true when your lower bound is a constant, which it is here. If that were a variable too, then we would subtract the lower bound plugged in. But the derivative of h, since we're doing this with respect to time, is h prime. So we have dv dt equals f of h times h prime, and we want to find that at the time when the height of the water is 5 feet. So if we come here, we just have f of h times h prime, f of 5, which you can find from a calculator, and then h prime is 0.26. F of 5 is just plug 5 into this function right here. Okay, so there's the work for that. Here's the work for the whole thing on one screen. Alrighty, number 2, the infamous banana problem. There were some pretty funny tweets back in the day about this problem after students took it. All right, so we have bananas are being removed at that rate, and then the workers are putting bananas back on the display at that rate. How many pounds of bananas are removed from the display table during the first 2 hours? So remember, the amount of change is the integral of the rate of change. So in this case, f of t dt from 0 to 2. Well, look, I even chose the same color. And then you can always round to 3 decimal places unless otherwise stated in the problem. Okay, part B. F prime of 7. So f prime. So you can just use math 8 functionality to find the derivative of this function at 7. And then using correct units, explain the meaning of f prime of 7. That's really the idea of this problem. So f prime of 7 is negative 8.120 pounds per hour squared. And what that is that's the rate of change of how fast the bananas are being removed by the customers. So it says after the store has been open for 7 hours, the rate at which customers are removing bananas is decreasing by 8.120 pounds per hour. So every hour, the rate is decreasing by 8.120 pounds per hour at the moment t equals 7. Okay, C, is the number of pounds of bananas on the display table increasing or decreasing at t equals 5? So here we'll just compare the two rates and see which one is bigger. So f of 5 is 13 something, g of 5 is 11 something. Since f of 5 is greater than g of 5 and f is how fast bananas are being removed, so bananas are being removed faster, therefore the number of pounds of bananas on the display table is decreasing. And then finally D is how many pounds of bananas are on the display table at t equals 8. Now this one's a little bit tricky, just be careful here. We have 50 bananas to start with, so you got to take that into account. So we have 50 bananas, plus how many bananas are getting taken away, which is 0 to 8 of f of t dt. And then the kind of tricky part here is the bananas aren't being added until 3 hours after the store has been open, which it says right here. So make sure you're reading the problem very carefully. So then we do plus the integral from 3 to 8 of g of t dt. And you can write it just like that and then use your calculator to actually calculate it. And so here's that work right there. And you should end up with 23.347 pounds of bananas. Number 3, so now there's no calculators on this problem. So we're given f prime and asked to find values of f. Remember, you find values of f from f prime by doing integrals. Since we know f of negative 2 is 7, we're going to use negative 2 as one of our bounds, and then we're going to use negative 6 as another bound, because that's what we're trying to find. So we do the integral from negative 6 to negative 2 of f prime of t dt. And that's going to equal f of negative 2 minus f of negative 6. That's how you do integrals. It's the antiderivative with the upper bound plugged in right here, minus the antiderivative with the lower bound plugged in. Okay? Now f of negative 2 is a known number. We know that value. This guy is what we're trying to find. And this thing right here we can calculate because we can just do the area under the curve from negative 6 to negative 2, which is just this triangle right here. Okay, so here's the work for that. So here's me plugging those numbers in. That triangle has an area of 4. And so you get 4 equals 7 minus f of negative 6. Solve that and you get f of negative 6 equals 3. And then f of 5 we're going to do the same way. Except now we're going to do the integral from negative 6 to 5 of f prime of t dt. And that is equal to f of 5 minus f of negative 6. Okay, f of 5 is what we're trying to find. Trying to find this. Oh, sorry, you don't want to go negative 6. You want to go negative 2. Sorry about that. I'm going to go negative 2. So just change this to a negative 2 here. All right, because, and that, again, that's because we know what f of negative 2 is. Okay, and then all those, this is all area. This integral right here is just the area from 5 to negative 2. I did this backwards, then I wrote it down right here on here, but that doesn't matter. All that does is switch the direction of this, and it changes our areas. If we go from 5 to negative 2, then stuff above the x-axis is negative and stuff below is positive. Okay, so it doesn't really matter which way you do that. Kind of good, actually, that you see both ways here. So when you go 5 to negative 2, or you can go negative 2 to 5, so that's this area, which is a quarter circle, and then you have this triangle right here. Okay. B, on what intervals is f increasing? Well, if you're looking at f prime, f is increasing when f prime is positive. So that's from here to here and there to there. And written in interval notation, you have this. Notice how it's closed on negative 6 because that's where it starts. I think you could technically close it on 5. Let's see what the rubric did on this one. I don't think it really matters in these cases. See, they even closed it here, which to me that never makes sense because those are the points where it's changing. So you could leave those open. I think it would be okay. Okay, find the absolute minimum value of f on the closed interval. So a minimum occurs when the derivative changes from negative to positive. That only happens right here, because here it's negative and then it switches to a positive value right there at 2. The other places to consider are the endpoints, but this endpoint, wherever it starts on the actual graph of f, from there you have a positive derivative value. Even though that derivative itself is decreasing, it's still above the x-axis. So it has a positive derivative, and therefore the function is increasing from there. So wherever that y value is to start, the graph goes up from there. So that's a min. Then over here, because that's all above the x-axis, wherever this graph ends, it's going to go up until it gets to that point. So that's also a max. But make sure you do, in fact, consider the endpoints on a closed interval because they are always either a max or a min. You just have to determine which. Since I just explained that those are both maximums, then the absolute min must be at negative 2, or sorry, at x equals 2, because that's the only min. Then it wants us to find that value. Okay, so here I said a minimum occurs where f prime changes from negative to positive, namely x equals 2. Both endpoints are maximums on f, so the absolute min is at x equals 2 to find the value of f of 2. Again, same thing we did above. So you do the integral from negative 2 to 2. And again, I'm choosing negative 2 because that's a known value right here. So you had to do the same thing 3 different times in this problem. Oops, keep switching the wrong thing. All right, and then on D, Find f double prime of negative 5 and f double prime of 3, or explain why it doesn't exist. F double prime of negative 5. So negative 5 is right here. That's just going to be the slope of that line because f double prime is the slope of f prime, which is the graph we're looking at. And then f double prime of 3, since there's a corner there, the derivative doesn't exist there, so f double prime of 3 does not exist. Now, if you look at the scoring rubric on this one, notice how they use this limit notation. This is just saying that the slope from one side is different than the slope from the other side. And I think you could just state it in words and say the slope from the left of 3, which is this statement, is equal to 2. You could say the slope from the right of 3 is equal to negative 1. And therefore, since those slopes are different, the slope does not exist at 3, and therefore the second derivative doesn't exist because we're looking at an f prime graph. Okay, but that's what they're getting at with the rubric right there, which may be a little confusing to look at. Number 4, the potato problem. All right, write an equation for a line tangent to the graph. So this is the question I was talking about here, where we have to find a tangent line, and then on part B we say if it's an underestimate or overestimate. And if you remember now, that's going to be all based on concavity, which we'll get to here in a second. So let's write an equation for the tangent line. Our slope is this, okay? And we're doing it at t equals 0. Notice, though, how there is no t in this problem. There's only an h, but we have this information right here, which when t is 0, h is 91. So we're actually plugging in 91 for h right here, and you get dh dt. Actually, I'll just zoom over to here. Nope, not there. And then you can see the work here and just pause it, save a little bit of time making the video. Okay, so this is me plugging in 91. And I didn't show the work here. I just plugged in 91 and got negative 16. So our derivative value is negative 16. And then we're going to use the point 0, 91 to write the equation of the tangent line. So you get h minus 91 equals negative 16 times t minus 0. Of course, you don't have to write the minus 0 in there, but I'm just showing you how the point slope form works. Then use this equation to approximate the internal temperature at t equals 3. So remember, we use tangent lines to approximate values of other functions. This is what the function essentially looks like as long as we're close to t equals 0. And t equals 3 for this problem is close enough. So we can just plug in 3 for t into this and solve for h to get our estimate. And you end up with 43 degrees Celsius. Okay. Use the second derivative to determine if it's an overestimate or an underestimate. So this is finding the derivative of this guy with respect to time. So you're doing negative 1/4. It's a constant, so we'll just leave it there. And so really we're just doing the derivative of the inside right here, which the derivative of h is h prime, or dh dt. The minus 27 has a derivative of 0, so it's gone. And then h prime is this entire thing. So I can put that back in place of h prime, and you get negative 1/4 from this constant right here. So that's that. And then instead of h prime, I'm going to rewrite all of this, which is negative 1/4 times h minus 27. Okay. And that then is 1/16 times h minus 27. And we're finding this at t equals 3, but we're using our tangent line at 0. I'm sorry, so we know from above we knew h of 3 right here was equal to 43. And so now we can plug 43 in for t, and here's the work for that. All we care is if it's positive or negative. That's a positive number, which means the function is concave up, and a concave up graph will always have tangent lines that are below it. Therefore, our tangent line approximation is an underestimate. Okay, and that's what's being said right there. And then part C, a bunch of jargon here. In the end, though, that just says find an expression for g of t, given dg dt. So we're given a derivative, we're finding the original function. This is separation of variables. Yet again, it's separation of variables even though there's no t in the problem. There's no t over here, right? But that's okay. We can still just have a dt by itself, whose antiderivative will simply be t. So this negative here, you can either leave it on the side with t or take it to the side with g. I'm going to take it to the side with g. So we get dg divided by, so I'm going to divide by this, leaving us a 1 on that side. So you get negative g minus 27 to the 2/3 equals 1, and then multiply both sides by dt, so 1 dt or just dt. All right, now we find antiderivative of both sides. So this is really negative g minus 27 to the negative 2/3 dg equals dt. So now we can do power rule, add 1 to our power and get us 1/3, which we divide by, so we're actually end up multiplying by 3, so it's negative 3 g minus 27 to the 1/3 power equals just t plus our some constant c. Okay. I was just checking that real quick. I felt like I made a mistake, but I didn't. And then we have an initial condition of 0, 91. So when g is 91 minus 27 to the 1/3 times negative 3, t is 0, so c is just equal to that. Okay, and then 91 minus 27 is 64. And 64 to the 1/3 is just 4, so we get c equals negative 12. Once you know your c value, plug it back into this part right here, and then we just solve for g. So you get negative 3 times g minus 27 to the 1/3 equals t minus 12. Divide by negative 3. So here we go, dividing by negative 3. Cube it to get rid of the 1/3 power. So I'm going to just save some time. Oops. Save some time here and just cube it. Got rid of the 1/3 power and then add 27. So you get g equals t minus 12 over 3 over negative 3 cubed plus 27. I wrote it a little differently here because I simplified some stuff. Let's see what the scoring rubric did on this one. They say you don't have to simplify things like that, so... Yeah, and they did not simplify, so they wrote it like I just did. That's my simplified version. And here's what I got. T minus 12 over negative 3 cubed. Notice, though, I do have all those being opposite signs, and they found a c value of 12. That's just because they left the negative on the side with t to begin with. If you see right here, a negative 1. Okay, either way, it doesn't matter. You can get c equals negative 12. Since all my things are opposite here, I have t minus 12 over negative 3. Remember, for a fraction, that's actually the same thing. Okay? All right. Number 5, we're looking at two different particles. We got position of one particle and velocity of another. Particle P, when is it moving to the left? So something is moving to the left when its derivative is negative, or its velocity is negative, and our velocity for function or particle P is the derivative of the position function. So the derivative of this is 1 over t squared minus 2t plus 10 times the derivative of the inside, 2t minus 2. Now this can actually never be 0. That's always positive, which you can try to factor or use quadratic formula and see that. It has no real zeros. So we only get a 0 from this one, which is at t equals 1. Okay, and then from there, we can make a sign chart, which I already have made here, so I'll just show it. So t equals 1 is my only critical point, and so then I'm picking a number less than 1, like 0. I plug 0 into here, and that's gone, and all that's gone, and so I get a negative value, which is how I got that, and therefore it's decreasing. And then pick a number bigger than 1, and you're going to end up with a positive value. Therefore, it's moving left on this interval where the derivative is negative, which is 0 to 1. Okay. Part B, find all times t during which the two particles travel in the same direction. So now we got to know when particle Q is traveling left and right. So this is just t minus 5 times t minus 3. This is the velocity function already, so I'm finding the critical points by finding where the velocity is either 0 or undefined. It's never going to be undefined because it's quadratic, so we have t equals 3 and 5 are our critical points. Make a sign chart for that. 3, 5, we'll call it v sub q, and then therefore position is x sub q. And I'm plugging in, like, let's say 2. I get a negative and a negative, which is a positive, so the function increases. Plug in 4, and I get a negative and a positive, which is negative, so it decreases. And then plug in something big, and you're going to get positive, positive, so it's positive and increases again. All right, so here's both of those sign charts on the same screen. We want to know when they're traveling the same direction, so that's when their velocities have the same sign. Okay, the purple one is negative up until 1, and this one's positive, so they're not the same there. Then this one's positive up until 3, and this one's positive everything after 1. So from 1 to 3, they're both positive, and then from 5 until it ends, they're both positive, which I believe was 8. Okay, so the particles move the same direction on 1, 3, and 5, 8 because that is where their velocities have the same sign. So we weren't just looking for positives there, we were looking for negatives as well. But this one was, the purple one was only negative here. And this one was, the green one was negative, not until after that. Okay, part C. Find the acceleration of particle Q. Is the speed increasing, decreasing, or neither? So the acceleration of Q is the derivative of velocity. So a sub q of t is equal to 2t minus 8. And we want that at 2, so you plug in 2. And you get negative 4. Okay. So that's what we have here. Now our velocity, if you want to know if a particle is moving, or if the speed is increasing or decreasing, you need to look at the velocity and the acceleration. If they are the same sign, then the speed is increasing, and if they're opposite signs, then the speed is decreasing. So then what we need is the velocity of particle Q at t equals 2. So I'm going to evaluate this at t equals 2. And that's going to be 4 minus 16 plus 15, which is positive 3. Okay, and here we can summarize this. At t equals 2, the speed of Q is decreasing because its velocity and acceleration have opposite signs. So you're looking for a velocity and acceleration being positive, both positive or both negative. That's an increase in speed. If they have opposite signs, one's positive, one's negative, then it's a decrease in speed. And then find the position of particle Q the first time it changes direction. So going back to this, particle Q first changes direction at 3. This was v sub q right here. Okay, so we're looking for the position of the particle at 3. Remember, position is integral of velocity, so we're going to do the integral from 0 to 3 of t squared minus 8t plus 15. That'll give us our displacement, and then you have to add in the initial position, which for q is 5. So you add in a 5, and then I'll show you the antiderivative here. So there's our antiderivative. Now, I didn't put the plus 5 in here to begin with. I found the displacement to be 18, and then did 18 plus 5 right there. And that's fine if you write it like that as well. And finally, number 6. I like this question a lot because we're analyzing a data table, a graph, and a function, and looking at derivatives and all sorts of different fun things. So in part A, it says find the slope of the line tangent to the graph of f at x equals pi. So the slope of a tangent line is just the derivative at pi. So we're going to find f prime. And the derivative of that is negative 2 sine of 2x. plus e to the sine x times cosine x. We evaluate this at x equals pi, which I'll do below. So sine of 2 pi is 0, which is nice. That's gone. Stuff like that usually happens on problems like this. And then we have sine of pi is also 0, so you get e to the 0, which is 1. So you end up with just cosine of pi, which is -1. Okay, handwritten key here. So there it is. Pretty much showed the same thing. On B, let k be this function and find k prime of pi. So now we got to do k prime. Derive the outside, h prime, keep the inside the same, times the derivative of the inside. Evaluate this at x equals pi. And what we need now is h prime of f of pi times f prime of pi. So we got to find f of pi. F is this function that we were given. We already know f prime of pi because we found it in part A. So that's -1. So this right here, that's -1. F of pi, we just got to plug pi into this. And we get cosine of 2 pi, which is 1, plus e to the sine of pi, which is 0, so e to the 0 is 1, and we get 2. And so you end up with, that's f of pi, so now we have h prime of 2. H prime we get by the graph, and so we need the slope at 2 right there. And so I had already found the equation for this line. The slope of that line, the line itself is -1/3 x, so the slope is -1/3. And so here's the final work. H prime of 2, which is -1/3, times -1 is +1/3. Okay, now we are going to find derivative of function m. This one uses product rule. So we do m prime, derivative of the outside, g prime, keep the inside the same, times the derivative of the inside, -2. So that's my u prime, and then times v, plus v prime, h prime of x, so this is using product rule, times u. Okay? So this right here is all my u prime, and then this was v, and then there's my plus sign in product rule, plus v prime times u right there. Okay, I'm going to erase those because they bother me when I'm trying to do the work. And we got to find that at 2. So m prime of 2 is equal to g prime of, I'm just plugging in 2 until everything, all the x's in the purple, g prime of -4 times -2 times h of -2 plus h prime of -2 times g of -4. Okay, now g is given in data tables, so g prime of 4, oh sorry, -4 is right here, -1. So you get -1 times -2 is just 2. H of -2 is the y value at -2 on this graph, which is right there, which is just 2. So you get 2 times 2 plus h prime of -2. Let me make sure I did that right. I think it should be h prime of 2 because I hesitated because h prime of -2 doesn't exist because it's a corner. So I think I made a mistake right here. Oh yeah, I just plugged in -2 instead of 2. Whoopsies. All right, so that makes more sense. H prime of 2, if you recall, that's just the slope right here, which we already found the slope of that line to be -1/3. So you get plus -1/3 times g of -4, which you get on the data table again. G of -4 is 5. So you get 4 minus 5/3, which is 12 thirds minus 5 thirds, so it should be 7 thirds in the end. Oh goodness, I made another mistake. Hold on. G of negative 4 is 5. Let's just look at this one. Oh, I did h of negative 2, and it should have been h of 2. I plugged in negative 2 instead of 2 for the h's. Sorry about that. All right, so this number right here, let me go back to my work so you can see. I called it h of negative 2 right here, and it should have been h of 2. And the y value at 2 is negative 2 thirds, which is what I'm showing right here. Yeah, sorry, I plugged in negative 2 for my x just into that part for some reason. All right. So you can ignore some of that work, but the explanation was good. I just used the wrong number. All right, and then finally, is there a number c such that g prime of c equals negative 4? Now, since we have values of g prime, it is potentially possible to use the intermediate value theorem here. And all we would look for is between negative 5 and 3, negative 5 and negative 3, if the g prime value ever changes from a number less than negative 4 to a number bigger than negative 4. And on these given values, it never happens. That doesn't mean it doesn't happen, because there's infinitely many values in between these that are unaccounted for. It just means we can't use intermediate value theorem to determine it. So therefore, this is a mean value theorem question. Let's find the slope between these 2 points, negative 5, 10, and negative 3, 2. So you get 10 minus 2 over negative 5 minus negative 3, which is 5 over negative 2. 8 over negative 2, which is negative 4. Okay? So we found the slope between 2 points to be negative 4. Therefore, the slope at a point must be negative 4. And you can look right here to see how I summarize that a little better and show my work very clearly. Make sure you're doing that. All right, that is it. Hope you learned a lot.